Let me propose a simple question. I have in front of me two boxes. Inside each box is either a red or a blue button. Now, we haven't opened these boxes or made any measurements of the buttons. But if I open one and record the color, can you tell me the color of the other button? Well, of course you can. In fact, faster than the speed of light, I know that the button in the other box is red. And it is. Now, this seems like simple logic. Well, yeah, if I have two options and I eliminate one of them, then I know the other one just by process of elimination. Even if I send one of these boxes to the other side of the universe, if I open it up and record it, I instantaneously know the contents of the other box. This shouldn't be. This violates Einstein's special of theory relativity, that nothing, not even information, can travel faster than the speed of light. So is the information just being rebellious? Does it just want to go against the man and break the law? Well, no. The reason for this is something called quantum entanglement, and in order to really understand it, we're going to have to cover some basics. First off, in the quantum realm, nothing really has to decide to be anything. It's like a young adolescent's future. It's uncertain. Until it is recorded. The button inside this box doesn't have to say it's red or blue. That is, until I observe it. When I observe it, I'm forcing it to make a decision. Being in all possible states at once is called a superposition. Back to our button analogy, in quantum mechanics, these buttons are both red and blue at the same time. That is, until I observe one, when I then instantaneously know the color of the other. We're going to take this up a level and pretend these buttons are electrons. Now, if these electrons are initially vibrating in unison, then they will always be in unison, no matter how far away they are from each other.
Seriously, no matter how far.
We know nothing about them except that they are paired. Although they may be separated by light years, there is always an invisible connection, called a Schrödinger wave, connecting both of them, like a piece of string. This connection is what we call quantum entanglement. Whatever happens to one automatically has an effect on the other, even over great distances. So, quantum entanglement is the concept that particles vibrating in coherence have some kind of deep connection. Talk about a long-distance relationship. It's so funny. Scientists today can use these bizarre properties to bring science fiction into science fact. We already can use this to essentially teleport photons and even entire cesium atoms. Not by dissolving it and zapping away to another planet like in Star Trek, but simply by transferring the information. Let me show you what one of these experiments would look like. Take atom A, who I will name Albert, and atom C, who I will name Carl. Let's say we wish to teleport information from Albert to Carl across the universe. First, bring in atom B, Bohr. Bohr is already entangled with Carl. Bohr and Carl are coherent. Let's make Albert come into contact with Bohr and scan him so that the information of Albert is transferred to Bohr. Since Bohr and Carl were already entangled, the information from Albert has now been teleported into Carl. The information of Carl and Albert are now identical, despite having never been in contact with each other. We have now transferred information across the universe instantly. One day, we may be able to use the properties of quantum mechanics to teleport more complex particles and molecules over long distances in no time at all. But until then, we continue to research the bizarre and curious quantum realm and explore the infinite horizon of human interest.